Welcome everyone to this AST webinar presentation. As you can hopefully see on your screen, I have a slight promotion today, and that is for our conference, the annual conference that the AST puts on, which is called CAST. This year, it's going to be back in Cocoa Beach, Florida, and from August 12th through 15th. If you are interested and have the opportunity to go to conferences, if your company provides that benefit for you, if you don't know if your company provides that benefit, you should definitely ask, because most companies do. CAST is a very, very unique and fun conference. It's small, it's about 200 people. It's very, there's a great level of interaction between the presenters and the folks participating. And so it's just generally a good time. You can use your phone and take a photo of that QR code and get additional details, get taken to the website so you can learn a little bit more about that. Promotion done. Okay, today our guest is Doug Hoffman. He is presenting on the topic of the often overlooked test oracle, the key to more powerful testing. So I'm really happy to have Doug. Doug has been around the AST for a long time. If any of you have taken our BBST foundations or the AST BBST courses, you probably know the name Doug Hoffman from at least 1 to 2 articles that are in there, maybe more. And several of his material is included in that presentation. So Doug has actually been working on computers since early punch card days. He spent years as a programmer before realizing how valuable and how much fun QA and testing can be. Since his earliest days using computers, he's strived to get the machine to do his work. And so he's done a lot of automated testing and found creative ways to find bugs in systems. A few years back, he thought about all the various ways he's tested verified test results and created lists of different mechanisms and approaches that he's used. He's been refining that list for years and years, and this presentation is basically about trying to summarize what he's figured out. So, Doug, I'm going to flip this over and make you the presenter. It's all you now.
Okay. Hopefully people can see the screen.
Yeah, and we're good.
Yeah. Well, good morning, afternoon, or evening, or night, as the case may be. In the next 45 minutes, I'm going to skim over material that I typically present in a 3 to 5 day class. So hold on, prepare for what my students have described as drinking from a fire hose. Lost that, okay. Okay, so a rhetorical question about software, the system under test. What can happen when there's a bug? Well, when there's a bug in the software, anything can happen. Anywhere. If the software can touch it, it can screw it up. So we're dealing with infinite numbers of possibilities here. A few background ideas before I get into the meat of today's talk about oracles. One way to think about testing is from the information perspective. Testing is a technical investigation of the product under test, and it's conducted to provide stakeholders with quality-related information. It's all about the information we get. When we design and run a test, our goal is to ask a question of the software. Are you broken like this? Our challenge isn't just creating and running a test, it's creating and running a test that tells us something interesting about the software. So let me describe what I define as a test. There are 3 parts to it. There's an exercise, there's a data gathering, and an analysis. The exercise set up before the test, and then we have steps and values that we input to stimulate the software. And along with that, we gather relevant data relevant being what we think is useful. It may be test specific, the results, for example. It may be independent of the test case. We may be looking at information that we are gathering about memory usage, for example. And it can occur before, during, and or after the exercise. Some of the stuff we may collect beforehand would be system variables, configuration information, and information about the software itself. And of course, the final goal is to analyze and determine whether the test has told us something interesting. Typically, I've found that people look at testing as an input, process, output model, that we provide the stimulation or the influences, the inputs, and the software does its thing, and then we get the results. It implies that we control all the inputs, and it implies that we can verify all the results. Well, the truth is a little bit different from that. We're not dealing with all the factors. There's data in memory and external data sets that influence the behavior and can be mucked with by bugs. There's program state. You've got to have the right screen up. You've got to have the right internal state to the program in order for it to behave properly. And there's system environment, the stuff that supports our application that we haven't dealt with. So I came up with what I call the expanded execution model. It has the input, process, output, of course, and also we have to consider the pre and post data sets because they both influence and are impacted by the software. The second time you add a user ID, you get a different response from the software than you did the first time. It tells you to pick another user ID instead of just entering it. Also, it's possible the software may make changes to other users in the database besides the one added. Remember, we're looking for bugs, and when one is encountered, strange things happen. The software also has to be in the right starting state. You get different behavior when you're logged in, when you're not. You need to be on the correct screen in order to order an item. The program state is not always visible. It's quite possible for the system to correctly reject the loan application for one user and then fail to reset the internal state variable and therefore reject all subsequent loan applications. Environment plays a critical role in the behavior of the software. How much memory is available, what services are available, what OS or browser you're using, and what the available network bandwidth is are a few of the millions of environmental factors that influence the behavior of the software. Have you ever had a timeout? Well, that's the environment. Likewise, memory leaks, soaking up all the network bandwidth, leaving scratch files around are examples of environmental outcomes. So with the expanded model, we have some implications. We don't control all the inputs, all the influences. We don't verify everything. Multiple domains are involved. It's not just our exercise. The test exercise actually is usually the easy part. And we can't verify everything. We can't even know all the factors. You know, it's almost a relief to realize that no test or tester can be perfect. A non-reproducible bug doesn't mean there is or isn't a bug. It means that some influence was not noticed and is different now. A bug that escapes to the field means we didn't check all the possible outcomes. We aren't wrong and we're not neglectful. It's only that we're not omnipotent. So in ancient Greece, there were temples for the various gods, and in some of them there were priests and priestesses called oracles who spoke for the gods. People would go to the oracles and ask them their burning questions to hear the answers from the gods. One of the most famous was the oracle at Delphi. A person would go to that oracle and ask a question of the priestess, who would in turn respond with the answer from the god Apollo, who, among other things, was the god of truth. And thus we've picked up the term oracle for the means to determine the outcome from a test. We're asking the god of testing. So for today, I'll define a test oracle as a mechanism or principle by which we determine whether or not the software under test is behaving reasonably. Unreasonable behavior requires investigation by a person. And when the oracle says that the behavior is unremarkable, we just move on. We don't second guess a pass on our tests. If it passed, okay, let's look at the ones that failed. So some notes on test oracles. Every test has some kind of oracle. The oracles that we actually implement may blend characteristics of multiple types of oracles that I will describe. We run multiple oracles on one test. We may check different kinds of behaviors. Did it go to the right screen? Did it update the database correctly? And those may be actually separate oracles. And when you add an oracle, the test gets stronger. And by stronger, that means the likelihood of finding a bug, if it's there, goes up. The more oracles we have, the more kinds of bugs we can find. The oracles may be independent of or integrated into a test. Often as we test, we're checking to see what's going on. Sometimes when we test, we may have a memory leak checker running. That's totally independent of our test, but it's an oracle nevertheless. And what I've discovered and what people who automate tests discover is that you have to have an oracle for it. And particularly when we start doing high volume testing, automation, then it's necessary to have good oracles. So we've got, let's see, types of comparisons. Basically, we have two ways we do comparisons. One's deterministic. A mismatch means the behavior is abnormal. We didn't get the expected results. This is the binary approach, pass, fail. And most of us doing testing and most of our tests use a deterministic approach. There's another approach, which is probabilistic. That indicates when behavior is warrants further investigation, but it doesn't necessarily mean we found a bug. It means that we need to look into this. And as I mentioned in the last slide, comparison is done within the test sometimes, and often it's a separate activity altogether. So I've then identified, yeah.
Yeah, can you expand on that a little bit? So you're saying that comparisons are done sometimes?
Well, sometimes the comparisons are done within the test. Sometimes we may create a log file, and after the test is complete, we go through to see, did the test do what we wanted it to do or what we expected? So the the comparison that we do, whether deterministic or probabilistic, is sometimes built into the test. My automated test, instead of creating a log as we execute, may read the next line of the expected log and do the comparison within the program. So I don't create a new log, I just read the old log so that I can catch the error at the moment that it occurs. Okay, so it's built into the test in that case.
Great, thank you.
So I came up with a baker's dozen of test oracles. And what I'm going to do now is go through and quickly describe each of these. These are distinct oracle approaches. We can, yeah. And as I said, a particular instance may be a blend, but each one of these is distinctive. The first is no oracle. Distinctly possible that the test itself just runs and we ignore the outcomes. This is really easy and the tests run really quickly, but we only notice spectacular events. The case here is that the system crashes or the application crashes. In one instance, my test set the printer on fire. People noticed that. But the no oracle strategy, we can do a whole lot of activities with no oracle and feel like we did something worthwhile, but it may be a false sense of accomplishment. The other extreme is an independent implementation. That is, we write the application or pieces of it, again, as the oracle. We may cover some range of inputs, some particular variables, some results, and we've implemented the actions of the software we're testing. So we generate correct results, and I put correct in quotes because software has bugs. And if we're creating a oracle, then it's software and it may have bugs. The independent implementation strategy is usually expensive and time consuming. And there's one factor here that we need to keep in mind. The more complex the oracle, the more likely it has bugs. And if it actually gets more complex than the software we're testing, then a miscompare is more likely to be a bug in the oracle than in the software we're testing. And our jobs aren't to debug oracles. So the first of the two types of consistency oracle is the saved master strategy. This oracle checks for changes, checks for differences between this run of the test and some other run of the test. It's the most frequently used automation strategy, and we have both validated and unvalidated masters. A validated master means we've gone through every character in that master file and have reason to believe it is really correct. Unvalidated is what we typically have, and that is we've gone through the file and didn't notice anything. IBM and their infinite wisdom actually went out to customers 2 years after a release to identify all of the bugs that had been found in the field to figure out whether or not their tests or actually why their tests didn't find those bugs. And when they looked back through their test results after 2 years, they found that 30% of the bugs that customers reported, they had uncovered. They just hadn't noticed that they were there. It's the most common method. The test generates a log of activity, and then we compare the log this time with the log last time, or we create a golden master, something that we may validate, and then we compare each run to that golden master. The second kind of consistency oracle is looking for differences, but we call it the functional equivalence strategy. We're typically using very high volume and some alternative program. A validated instance would be, for example, testing spreadsheets. And if you compare against the behavior of Excel, by definition, Excel is right. Even when it's wrong, it's right. Your spreadsheet better do the same thing. So we have a trusted oracle there. And unvalidated, if we're testing the spreadsheet, we may use OpenOffice spreadsheet. And if there's a miscompare, we may have a bug. We may have a bug in the OpenOffice. So typically, go ahead.
Someone is asking, is a golden, in your description of a golden master, is that sort of the same as a benchmark?
It can be. It can be. It depends on how you're using the benchmark. If it's a set of activities that if you deviate from that benchmark, it means that you have encountered a bug, then yeah, it's a golden master approach. Okay?
Yep, thank you.
Okay, so the functional equivalence, we're testing against a competing product or another version of the software. For example, our software on another platform. We want to compare the results, and if they're different, then we found something that is likely to be a bug. So we just feed test data into the software and the similar product and compare the results. So the first of what I think are more interesting oracles is the self-verifying data. The oracles so far you're probably familiar with. They're fairly common. The self-verifying data builds the expected outcomes into the data. And there's three basic ways I've found. One is self-descriptive data. Another is a cyclic algorithm. I was doing data communications testing and wanted to send random data and random packet sizes, but the line was half duplex at that time, and therefore I didn't want to take twice as long to run the test. I wanted to be able to send the data and check it at the far end. And so by using a random number generator for the first value and an increment between values and some count of values, number of bytes that we'd have or number of values that we'd have, I can append that to the data itself, and at the far end, by using the start, increment, and count, can identify exactly what should have come down the line. The third and I think most interesting way is a shared key with algorithms. So we generate the random record, the data in the fields from a seed value. If you're familiar with the random number generators on computers, they're called pseudo-random number generators. They will generate the exact same sequence of statistically random numbers. If you have a key or seed value to start with, you'll get exactly the same series of random numbers. So if we embed the key with the record that we've generated, person's name, address, telephone numbers, we can write a program that will generate records of that kind of information. And if we have the seed, we can identify what that record should contain. So we embed the key, and then we use the algorithm and key to identify as the oracle. This is what should be the answer. Another interesting approach is a model-based strategy. And the way we do this is we identify and describe some aspect of the software that's a state machine. The menu tree of an application can be described as a state machine. Each window is a state, and the events are what we do in that window that'll take us to another state, another window. So we can identify the states and the events and put that into a machine readable model. And then we design our tests that read in that state machine and do whatever the test is designed to do to get from this place to that place. And so we're reading and applying the model. Each time we make a transition or don't make a transition, we can check to see did what happened actually match what the model says it should happen. And we can update the model as needed as the code changes. I've used this in testing front panel operations for a family of products. So we could write the test for setting the clock, and by reading in the state model for the various devices, the same test works with each device. The next is constraint-based. Here, we're looking for individual values or characteristics that have constraints, limits on the values, 256 character names, or the maximum integer value. And so the constraint-based strategy, we're writing our tests and looking for, as an oracle, that we are maintaining those constraints. Often we have the variables that constrain one another. And an example of this is the spreadsheet. The number of active cells you can have in a spreadsheet is limited. Maybe 65,000, for example. Well, that means that the number of rows times the number of columns has to be less than that. If we add rows, we've constrained the number of columns. And so our oracle may check to see if the number of cells specified is correct or not correct. The size, form, type, etc., for some applications can be used to constrain one another. The page width is limited, and so the size and of the print and the type font define what we can put on that page. One constrains the other. And we have constraints like invariant rules. I better have been born before I got hired. And if that's violated, we have some problem in our data set or in our application. So the way we use this, we just confirm conformance. And I don't think I've defined synchronous and asynchronous checking. So synchronous checking is checking that's done along with the test at the same time, and usually as part of the test itself. So it's synchronized with the activity of the test. Asynchronous checking is independent of what's going on. And a good example here is memory leak checks. But we can also do things like database integrity checks that we run just in a loop to make sure that the database links, the internal links, are kept consistent and we don't have bugs in the engine itself. I was working for a database company. And the checking may be specific or independent. As I said, those two examples, one is specific and one is independent of the tests. The next is a probabilistic strategy. We're looking for relationships that usually but don't always hold. So here, an approximation, the heuristic or a rule of thumb, partial information that supports but not necessarily mandates the conclusion. Error in this case means it probably is a problem. And an example here is that an employee is usually older than their dependents. But there are exceptions possible. But if you find a case in your data set that the dependent is older, it's worth looking into. At the company Oracle, one point in time, they actually checked the length of time it took to run each test. And if it was faster than 1/3 of that time, or took longer than 3 times as long as the last time it ran, they looked into it. And about half the time, there was a bug. The test actually passed, but there was a bug in the code. We weren't doing something that we should have, or we were doing a whole bunch of stuff we weren't supposed to be doing. The computational strategy, the principal idea here is that for some things we're testing, we can actually run an inverse or reverse function to identify whether or not these results could be the consequence of the inputs that we used. And so basically what we're doing is the reversal function. If we split a table, we merge tables. And we compute from the results, we compute possible values for the inputs and then check to see that the actual inputs are in that set. Here we are subject to common mode errors because usually the function we're using to reverse it has some code in common with the function that we're testing. And so if there's a bug in that common code, we may end up undoing the error when we do the reverse computation. And it can miss obvious errors. The square root of 4 is 2, not -2. But the square root function could give us -2, and we square it in order to see whether or not the square root function is working. So there are some drawbacks to a computational strategy. The statistical strategy, this one is pretty interesting. It's rarely used and is not for the math phobic, but it's a reasonable way to test some very complex systems. Some applications can be characterized statistically. Let me use the example here of sales taxes. The sales tax can be computed by knowing where the orders originate, because the sales taxes are location dependent, and the amount of each order. But there are a lot of different places, and therefore a lot of different taxes, tax rates. And so it's impractical to walk through all of the locations and then check the tax computations. But it's also impractical to check the correctness of an arbitrarily, a randomly selected order without creating a copy of the application itself. So the statistical strategy might be used in order to do massive test case execution. We can relate the population statistics for the locations and the population statistics for the amounts of the tax rate, and we can relate that to the population statistics for the resulting tax amounts. If we generate random orders with known statistical characteristics for the locations, and similarly known statistical distribution of the amounts, we can predict statistically what the taxes should be. So we can measure the statistics of the resulting taxes and identify whether or not they are a logical outcome of the inputs. We can do massive numbers of random orders and give us a feel for whether or not the software is working. This involves complex statistical mathematics, but we can generate gazillions of statistically distributed orders and know that the population statistics we get from the taxes without checking each order. Property-based, we use a secondary characteristic of a test or a variable or variables. We compare coincidentally correlated relationships. They're not necessarily complete, not necessarily causal, but some examples, sales order number should be in time sequence order. So if we sort the sales orders by number, we should get the same order, all of the same orders that we get in sorting by the time of the timestamp on the orders. I've also checked the property of a printer test by looking at the number of pages that it printed. You know, if the print test is supposed to generate 3 pages and it generates some other number of pages, then we got a problem. And so we can do a property-based oracle. And another example I've used, US zip code is either 5 or 9 digits. If it has a character in it, it's wrong. If it's not 5 digits or 9 digits, it's wrong. And I use this to test a database unload load, where we were checking to see, did we lose a character or shift by a bit or a byte? Okay. Oh, another example that I've written about on property-based is an article on heuristic oracles. And I was checking for discontinuities in a sine wave, the sine function. The characteristic that the values increase or decrease between the high and low, between the minima and maxima. So if we generate the sine of x and then take the sine of x plus some little amount and then add a little amount to that and a little amount to that, we should find that the results come back that they steadily increase or decrease depending on which half of the wave you're on. And the only exception is when it gets to the minimum or maximum. Diagnostic strategy, we're actually getting into white box testing here because we're tracking the execution of the code using the code assertions. So we insert assertions or logging of the activities, tracing of the program. And then we run the tests and the assertions check themselves, or we generate a log of execution and we can cull through that to look for errors. Code assertions, you can't get there from here. You have to be logged in with a valid user ID in order to buy something. And the other method, we put print statements into the code that might identify the values going into a branch, so that we can find out that this branch did not go to the right place, and here are the values that went into it. So we can see that it's not the code itself, but it's the values that were input there. We have to trace back to figure out how the values got out of whack. These last two are not often used for automated tests. So the input and results are specified together. When we choose one, we're choosing the other based on this is easy or well known. We carefully craft the input values to match with the expected result. In these cases, the oracle's frequently built into the test because they're so closely aligned. And it's often taken for manual regression tests in complex software. My brother-in-law worked for an organization and he was testing a program that tries to predict what happens when atomic particles collide. Is there a chain reaction? What other particles are being generated? You want to simulate that as closely as possible before you actually collide the particles, because if there is a chain reaction, it can be damaging to your accelerator and the 5 miles or so radius from that. And so you want to be fairly confident that it isn't going to happen. The test program itself takes 2 days to run on the supercomputers. So we want to know exactly what input and exactly what to expect in our test. And the human oracle, yeah, the most common one, you set a person in front of the software to observe what's going on. The human uses their judgment to decide the verdict. In this case, we are actually an oracle on many different levels. We are multiple oracles at once. It works for manual or automated exercises, although automated exercises, it's hard to look at a million individual results. And it works for scripted or even unscripted tests, doing random walks. The computer that we have between our ears is still the most powerful computer that we know of. People with AI are trying to get past that, but in general, we are a whole lot more flexible. And one note here, a human oracle is applied whenever we think there may be a bug, because it takes a human to investigate. We haven't figured out how to automatically do that without having to have a human double check. And I'm not sure we'll ever get to that point. Whew. So, recapping, all tests use oracles. There are many types of oracles. I've identified a baker's dozen. It's impossible to check everything. We don't control all of the inputs, all of the influences on our software. Oracles don't need to be deterministic to be useful. Myers wrote that in order to have a good test, you must have a known result. Well, at the time, that may have been true, but non-deterministic application or oracles can be very useful, and you don't necessarily need to know what the exact answers should be. And we have oracles that are independent of the tests themselves. It's not just that 2 + 2 = 4, it's that 2 + 2 = 4, and we didn't touch the network, and we didn't leave files around. We didn't interfere with the action of other programs that are running. So you've been fire hosed, and I'm sure that there are questions out there.
Yeah, that was good. You're right. That's a lot of information, especially with a baker's dozen of oracles. But so there are a few questions, and if anyone has any more, please just go ahead and put them in there in the questions panel. So the first one is a smoke test a form of no oracle?
Well, it depends on whether or not you're checking results. A smoke test can have individual test cases. I like to describe it as hello world for every individual function. And it may be no oracle in the sense that you're just touching the function and don't care what the response is. You have no oracle. But sometimes you're actually checking the response.
So another question is, could you clarify the difference between constraint-based oracles and property-based oracles?
It's subtle. Let me run back here to so in a property-based strategy, it's not necessarily a constraint. The sales order number being in a time sequence order is a property. So you can sort by sales order, and you can sort by the time the order was entered. Checking the number of pages printed by a test, that's not a constraint, that's a property. So, person who asked that question, did I address it?
We'll wait for confirmation on that.
Okay, so what's the next question? I can come back to this.
Yeah, so the next question is, so you said that diagnostic strategy was more of a white box approach to more of a white box strategy. And then, oh, so the person confirmed that. That works for us, thanks. And so you said the diagnostic was more of a white box, which is basically knowing more about the code. So are some oracles more white box or some more black box? How do you sort of divide those?
Right. So I define white box testing or glass box testing as testing based on knowledge of the code. So based on having looked at the code, I design a test for the code. I want to get to this place in the code with these values and see that that's true. That's white box testing. Once I create that test, I may run it in a black box fashion, but the design of that test is based on knowledge of the internals. A black box test, we're just looking at the externals. We know that it's supposed to do this, so we give it the input, and we don't care how it does it. It processes it, and we look at the result. That's a black box. Here, we're actually instrumenting the code. So we have to open up the code and look at the code, and our tests are based on that code. We're plugging in instructions into the code in order to test it.
Great. So another question is, another example of computational strategy, translating text into another language using an online translator and then back to English, would that be?
Yeah, that's called round tripping. And yeah, that is a computational oracle. And I've used it, and the results can be hilarious because in the case of translators, they may be lossy functions. And by lossy, meaning some of the information is thrown away. The language may not have the future tense, and therefore whatever you said when translated into that language and then translated back can't be identical. Information was lost in translation.
Great. So just a few more questions. Let's get those in, and then we'll try and wrap up in a few minutes. But so, Doug, you had said that the last two examples of handcrafted and human oracles, they're not really used much in test automation. Are there other? So are some of the oracles more likely to be used, and so where or which ones? Really?
Yeah, any of the other oracles are likely to be used. And what I found is that when you do a massive set of activity, right, massive random walks, you use one or more of the oracles. And depending on the application, different oracles may be applied. So all of them except handcrafted and human. And there are cases where you may handcraft a whole bunch. We may generate a table of inputs and expected results, and we may have a function that will generate those combinations to test some aspect, some subset of what our application does. And so we may use a handcrafted approach where we're selecting the inputs and outputs together. And James Bach taught me about a blink test, where you run huge number of inputs and watch an output field, for example, and you can spot if there are exceptions, that you get a negative time. So it's computing the duration of meetings, and if you see a negative amount of time, then either the inputs were not correct and accepted, or the computations are not correct. So a human oracle is used in that case with a massive number of inputs.
Great. So I think that's all the questions that we have. Can you actually go to your last slide, not the wrap-up slide?
Yeah.
And then so that's it. So thanks everyone for coming. Doug, did you? Is there a way that people can contact you if they have more questions?
Yes. Did I put that?
Was that actually on the first slide? I think. There we go.
Yeah. So, yeah, doug.hoffman@acm.org. And let Chris know if you have interest in hearing more about one or another, or never hearing from me again.
Yeah, that's a very good point. If you are interested, if this is a topic that interests you, or there are other topics as well, please let us know, because we do like having these webinars, and we like being able to bring content to the community and be able to put them up there for anyone to have. So I just want to say thanks to Doug. Thank you for joining us, and also thank you for presenting, rather. And then thanks everyone for who joined. This concludes our webinar. Thanks everyone.